do is I'll give you some lead on how to do the assignment, the current problem. Okay. So one which needs application of Kirchhoff's current law. So you have, let's say, an example is you have this circuit. So here your goal is find the transfer function VC of S divided by P of S. So you are using Kirchhoff's current. Similar to what you do for Kirchhoff's voltage law, you first have to write the impedances and the inputs and outputs. So what we'll do is we'll say the current going through here, we'll denote this as I R1 of T. We'll denote this as node 1. This is node 2. Okay? The current going through this, we'll denote this current as IL of T. The current going through this as I R2 of T. And of course, the current going through this as I C of T.
The current for R2 is going to the left, right?
It's this direction, to the right.
Oh.
So what is the current going to here? It will still be I R1. You can always say this is node 1, node 3, but you don't really need that for now. You really need node 1 and node 2.
Isn't the node is any point where at least three joints done?
Where, yes, so here it's where the current gets split, or where current gets split. Okay? So here, although there are three, there are only one. You still need to consider this because you're solving for this. Okay? You're trying to solve for this. So the current going through here, it doesn't get split. The current going through this is the same as this. So you can say IC is IR2. Okay? We can do that. That's fine. But you still need to consider this as node. You can say IR2 is equal to IC. That will give you one more equation. Got it? Now if you write the impedances and the inputs, so you'll get this as I R1 of S. Okay? I won't confuse you guys, so let me not. This is not relevant. This is I L of S. I R2 of S. This is I C of S. This is the output. The impedance this here is Ls. The impedance here is, I'll just put this in, the impedance is in Laplace of input output are in bracket or in boxes. Okay? This is Vs input. This is again output. Here it is R2, the same thing, the impedance. The impedance again here is R1. Okay. This one is Vc of S, and the impedance is, let's say if this is C, 1 over C.
Maybe 1 over C is
1 over C, yes.
So, there are two components there where it is C and V.
Now this, see what is happening is, so what this means is, there is nothing extra here. If you measured the voltage across this, you would call it VL of S.
The voltage across what?
Across the impedance L. You can measure voltage. So what you can measure is there is current flowing right, through here. If the current, you multiply the current by the impedance, you're going to get the voltage. There is always voltage. This is the output, input voltage. Okay, and this what when you voltage gets dissipated. You understand dissipated? It's output. Dissipated in the sense output.
What?
It's consuming some power here. This is consuming some power. 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 We're only interested in knowing what is the power, what is the voltage consumed by this. So we have to see this VC of S. Okay? VC of S into IC of S will give me the power consumption of this particular capacitor.
Shouldn't that V of S have a circle around it since that's the input?
Which one?
The only V of, that's the input, so shouldn't it have a circle?
It doesn't matter. So input, output. So here you have the circle here.
Okay.
Okay. So these or everything in boxes are impedances.
Oh.
Impedances are Laplace of input output. So you do impedances plus input and output, right? So you have the transfer function. What you do is you do nodal analysis. Nodal analysis. Let's do node 1 first. So what you want to see in node 1 is I write it in terms of impedances or Laplace equivalence. I R1 of S would be equal to I R2 of S plus I L of S. Okay. this current gets split.
Oh, yes.
The current going through this, when you apply this voltage, there's a current going through here, and the current gets split in this and this direction. Okay? Now, so what you need to do is here, see this is, you can say, let's also do node 2. Node 2 is simply IR2 of S is equal to I C. Okay?
Wait, no.
So the current going through this
Oh, yeah.
is the same as current going through this.
Because you said there's no
That's
split.
right. So there is a node here. So what you Kirchhoff's current law says is current going in is equal to current going out. So these are your driving equations. Okay? You have to get the transfer function from these two equations. So how do we do that? Now, what is IR1 of S?
IR2 plus ILFS.
See, if you look at what your V of S is, V of S is, you can say, V R1 of S plus V L of S. Okay, this is from Kirchhoff's voltage law. Okay. For mesh 1,
Okay, I'm a little confused.
alright, let's not do this. This you should not be confused with. There is nothing. Voltage law, how do you apply voltage law? If you consider this as mesh 1, this voltage would be equal to this voltage plus this voltage. And whatever voltage is here, that will get split into this voltage plus this voltage. Okay? So you do this. You can say this is simply equal to V L of S. Okay? Divided by Ls. And your V L of S is the voltage across this one. Say voltage across this one is V L of S. Just like voltage across this one is Vc of S, voltage across this can be represented as the voltage dissipated, voltage output can be represented as VL of S. Okay? What do you do if you're trying to do voltage across this? You do Ls into IL of S, right? You remember? That's what you would have done. So VL of S is this voltage across this component, voltage dissipated across this component. Every component has voltage dissipation, voltage output, and it's simply equal to the current into the impedance of that. So what is voltage across this one? Voltage dissipated across this one.
VR2.
What is it equal to?
IR2 times the impedance.
Right. So IR2S into R2. You get it? So you have this. So here we don't have to do that for this particular so I can write this as V of S minus VL of S divided by R1 is equal to IC of S plus VL of S divided by Fs. Okay. What is voltage across this? IR1 times R1, right?
Yeah.
IR1 times R1. You see?
I see that using equal IR for that, which you just said, but I don't see the.
What is this numerator? Here, VR1 is simply equal to V of S minus VL of S. This is your Kirchhoff's voltage law. What happens is, when you have a circuit, when you have voltage applied, will get split into this and this. Okay? How do you apply Kirchhoff's voltage law to this mesh, first mesh?
Voltage around the loop is equal to 0. So how all the voltage equals 0.
Right, so this is what that is. V is the input, this is the first output, this is the second output. Okay, so I've just written this here like this. Right? So you can see
That's it, node 1, right?
Hmm?
That's at node 1. Then it goes to that node.
no, I'm just for this is for node 1. So let me put rewriting node 1, you're going to get V R1 of S divided by R1. So you understand, you agree with this? This is clear? I've just written this is just Ohm's law. Okay?
It's which law?
Ohm's law, V equal to IR.
So you didn't talk. Okay.
I mean, see, this is, you should be able to understand this. If you don't understand this, then it is difficult for you. Keep going.
So the one, the VLS,
Hmm.
I
That is
guess,
also Ohm's law.
but that L is not, V equals IR, that's not a, that L is not a resistor.
Right, so Ohm's law for resistor, what is it? V equal to IR. What is it for inductor? So if you're talking in terms of temperature, ILS.
Oh,
For capacitance, it is I 1 over Cs.
okay. Knowledge.
This is the Ohm's law. That is what, see, you're not looking at the table. I told you to look at the table. Study that table if you want to understand. It's a very simple implementation of Ohm's law. this is Ohm's law. Again, I can do the same thing here. IR2 is what? VR2 over R2 plus V LS over EL. Okay, so this VR1 is what? V of S minus V divided by. Okay. Now here what I'll do is I won't use this. I'll just skip this and just keep it as IR2 because what I want to do is I want to just use IC. Because from node 2 equation. Okay, IR2 is IC here, node 2 equation. IC of S. Right? Clear? Is it clear? Making sense?
So far.
Okay. So what is IC of S here? We have V of S minus VL of S divided by R1 is equal to CS into IC into VC of S. Plus VL of S divided by L. So everything now we have written in terms of voltage. Now look at it, look for here. What do you need to eliminate? See what is everything here is either known quantity or input or output, except one quantity, which is neither a known quantity nor an input nor an output. What is this V of S? It's an input. This is a known quantity. This is a known quantity, C. VC is,
That's output.
that's the output. This is a known quantity. VL of S is the only one which does not qualify as input, output, or known quantity. Okay? How do you eliminate VL of S? What is VL of S?
That's the voltage at that, I forgot what you call it, that squiggly thing. That's the inductor.
VL of S is the voltage across this. Okay? This voltage now gets split into this and this. See what happens is how you have to understand how current works. How is this dissipated? Whatever voltage this particular node has, this will be applied across the switch. How do you come up with the Kirchhoff's voltage law for this mesh. How do you write the Kirchhoff's voltage law for this mesh?
For the second mesh, so it would be, well, it's the sum of all equal to 0, so you just add the VLS to the, all the
Does
voltage.
VLS plus VCS minus the voltage at that R2?
Why minus there?
No, you add them all. The sum of all will equal to 0. In
No,
that.
but that.
It will be sum of all will be equal to 0. Okay? Because there is no applied voltage.
So, then wouldn't VLS be equal to minus them other two voltages?
VL of S, what would it be?
I'm saying VLS could be equal to V minus VC of S minus that other voltage, the VR1 of S. I mean VR2 of S.
So here, VL of S can be written as V R2. Okay. So we have to introduce a term called admittance. You know what admittance is? What is admittance?
It's whatever's in the last column.
Can I pull the book up on the
Yeah?
Can I pull the book up on the
Okay.
so you can see it?
You got it?
Yeah.
Chat two. Keep going. Yeah, electrical network. Everybody can see that? So this is, you have to understand this, okay? It's very simple actually. This is the voltage current relationship. This is, what law is this? This is Ohm's law in time domain.
Ohm's law on what?
In time domain, expressed as a function of time. Okay? This is still Ohm's law. It's just expressed as current. Okay? This is expressed as charge. What is charge? How do you express charge? What is the relationship between charge and current? Alright, let's forget about this thing. Okay, charge is nothing but integration of current flowing between a certain time, between time 1 and time 2. Current is rate, correct? Current is rate of flow. So if you integrate this between this thing, you're going to get, if you see this thing, what is it? It's simply, current is this thing. If you differentiate this, you're going to get this. If you differentiate this equation, you get this charge. But you don't have to worry about it. Okay? So don't worry about this for now. Just look at this. This column is very convenient. Okay? This is just the impedance. We have been talking about this impedance all the time. The impedance is nothing but voltage over current. If you take the Laplace of this and do voltage over to this current, what is the Laplace of this? What is the Laplace of that equation? How do you express the Laplace of that? You have V of t equal to 1c integral of I e dt, right? So this is what? V s 1 over cs I of s. What is the Laplace of this? V, so this L di of t dt. What is the Laplace of this? V is equal to Vs equal to Ls I of s. I of s. Correct? You follow this? Just like when you differentiate, an s gets added in the numerator. If you differentiate an integral, an s gets added in the denominator. You see the pattern? That's it. So now what is the impedance? Impedance is nothing but you take I of s on the left hand side. So if you take V of s over I of s, it is L of s. You see L of s over there. If you take V of s over I of s, what is the impedance you see there? 1 over cs. That is impedance. That's nothing but that. Okay? So admittance is what? Now what is admittance? Impedance is what? What do you understand by impedance?
Voltage over current.
Huh?
Voltage over current.
Huh?
Voltage over current.
No, what you understand by impedance. What does impedance do? What is impedance? Impedance is resistance to flow of current. You understand? The resistance offered. What will have a high impedance? And a insulator will have a high impedance. Right? Impedance is a general term used for resistance to flow of current. See, all these three are impedances. Those mean it will resist the flow of current. What is admittance? It's a reciprocal of it.
Just a what?
Reciprocal.
Oh.
You understand the difference now? It's nothing but reciprocal.
What do you mean, like impedance?
Definition.
So if there is resistance, what is the non-resistance? So let it easily flow. So that is the term is called admittance.
So if the impedance on anything like the applied impedance, it cancels out and then makes it so easy.
So it's like you have a pipe, right? The smaller the diameter of the pipe, the more resistance, right? What is the admittance? A larger diameter.
So by definition, admittance is the non-resistance to the flow of current.
The higher the admittance, the easy the flow of current will be. You get it? It's simple. It's not that difficult. Admittance is a function of what? Resistance is a function of what? They are not function of current. What is resistance a function of? Resistance is a function of. Resistance varies as what? Resistance is a function of the material. Resistance is a function of the. See, you're just throwing stuff out there. Don't just throw stuff out there.
The density of.
Not density, the cross-sectional area, the length, the temperature. If temperature of something increases, what happens?
Increase in current.
Current is always a function of how much voltage you apply. Temperature increases, resistance increases. Resistance is a material property. Resistance of anything, electrical resistance of anything is a material property. Will current flow through this? Regardless of how big you make this, will current flow through this? Not really as much. Because it's a property, that's material will not allow current to flow through this. First of all, the resistance is a function of the material itself. Then if you take the same material, if you take copper, right? If you have a bigger copper wire, the resistance will be less or more. It will be less.
You mean bigger, you mean like diameter or length?
Diameter.
Okay, but as you said, like lengthwise.
Lengthwise, it will be, if you take a longer copper wire of the same cross section, the resistance will be
More.
more. If you take the same length, if the diameter is big, if the cross section area is big, electrons can flow. It's if you have to think about flow of electrons as flow of fluid particles. Okay. So this one you have to just complete this. Try to complete this. It's simple. Okay. You understand this. I'll give you this and you can solve this. So here I can write this as V of S minus VL of S divided by R1. This is nothing but V C of S divided by let's keep this as R2. Okay. This is B So what we are doing is, see, whatever voltage is applied here, it actually gets split into this and this. Now, just think about what you're doing when you're doing the voltage law. When you're doing the voltage law, what is the direction of current? It's flowing like this. It's flowing opposite to this. You know that? You realize that? So when you do this, you're just saying V. This is V L of S is equal to V C of S plus V R of S. This is voltage law if current is flowing in this direction instead of up. When you assume current flow in meshes, you assume it is flowing up, right? That's when you add all of them and say equal to 0. But if current was flowing up, correct? If it was flowing clockwise, when it comes here, it flows in this direction. That's when you just add up and say equal to 0. If current is flowing in this direction, this quantity will become negative. And that's what you see. Okay? So this is from node 1, and node 2, you can say, what is this again? Simply V L of S minus V C of S divided by R2 equal to, this is simply V C of S divided by this is multiplied by C. Okay? Because divided by just a minute. Okay? You do this. Now what you can do is from A and B, solve for VL of S. Or take B, solve for VL of S, and substitute that VL of S here. The only known quantity, only unknown quantity between these two is what? VL of S. Everything is either a known quantity or something you are trying to find. Okay, you can then figure out this VC of S over